Okay, so we're recording. Okay, so today I wanted to talk about this result, which is a paper that appeared last week on Archive. It is a collaboration, especially with Alessio Belenchia, who is now in Germany, and Mauro Paternostro. So there is a overall 3 papers discussing this topic that I'm going to talk about, but our newest contribution is this one, and I want to focus on this one, which I think is very nice. So this was the first one, and it deals only with like Gaussian stuff, continuous variable Gaussian stuff. This is an experimental paper, and this one generalizes it to any kind of system, so it can be qubits or anything like that. So it greatly generalizes the previous results. Yeah, and in the end, I'll talk about this experimental paper as well, which was an experiment done in Copenhagen. So this is like the picture we have in mind for the types of problems we're going to consider. So we call these the continuously measured collisional models. So the typical scenario we have in mind is a quantum optical setup where you have a cavity, an optical cavity, and there's some system inside. And you pump some photons through the cavity, but this mirror is like semi-transparent, and so some photons leak out. And so the idea is that you're constantly monitoring the system. So the system X here is being constantly monitored by reading out these photons. And the idea is that this kind of process can be mapped into a collisional model where in each time step, the system only interacts with a small ancilla, so like a small subsystem, Y. And so X interacts with Y, and it comes in, and then it flies away, and we measure Y. So the system is interacting with this environment, and we monitor the environment. And the typical circuit diagram will look either like this or like this. This is actually, the 2 pictures are equivalent. It's just different ways of drawing them. So the idea is that, the system interacts with the first ancilla, and then we measure the first ancilla. So this gives us a classical outcome, Z, which you can think about this as being, for instance, 0 or 1 or something like that, like just a classical outcome of your measurement, right? So this is a quantum system, this is a quantum system, but after you measure it, you get just a number. And then X moves on, interacts with another ancilla, you measure the other ancilla, and so on, right? And then what you get is essentially a measurement record. So you have the Z, which are the individual outcomes, and you get this zeta, which is the measurement tape, is like the entire record, so like a bunch of zeros and ones. Right, and I emphasize this because it will be important that we distinguish between what is the meaning of Z and what is the meaning of zeta. Z is just the bit of information that you get from one measurement, and zeta is the accumulated information, right? So this zeta of t is like an accumulated information about the system. Yeah, so that's the basic idea. Now let me talk a little bit about how we actually model that in terms of dynamics. So we have to distinguish between conditional and unconditional dynamics. This will be the big feature of our framework. So unconditional means that the system interacted with the ancilla, but you don't measure the ancilla. And conditional is what you get when you measure the ancilla. So just to clarify this a little bit, in some papers, people tend to view this interaction with the ancilla as kind of a probe that you want to measure the system. And so ideally, you would like this probe to never introduce any noise in the system, because since the system is quantum, when this ancilla interacts with X, it will cause some back action that will change the state of X. And in some papers, people view this as a kind of a bad thing, as a deleterious effect. Here, we're not really taking this viewpoint. So we think about this interaction as it's going to happen whether you like it or not. So this interaction between X and Y, it will happen, and there's nothing you can do about it. The question that we want to address is, what difference does it make if we measure y in the end or not? That's the key question. So x will interact with y, but we can choose to measure y or not. And the question is how much more information we can learn about the system if we measure y. So the unconditional dynamics is what happens when you don't measure y. So you don't measure. And in this case, the dynamics will be given by this stroboscopic map, where at each time step, the system couples with an ancilla via some unitary u, and then you trace the ancilla and you get the updated state of the system. So it's this discrete time dynamics. The conditional dynamics, on the other hand, will be given by this map, where this zeta is the measurement record. So here, it's a little bit more complicated. So you have the system and t ancillas, right? So x initially times 0, and then y1 up to yt. And then you alternate. So you apply a unitary, and then you measure ancilla 1. Then you apply another unitary, and you measure ancilla 2, and so on. So for instance, this unitary u1, it will only have support over these two states, right? So u1 only acts here and here, whereas z1 only acts here, right? Because you're only measuring the ancilla. So the unitaries couple system with ancilla, the measurements occur only in the ancillas. But since there's always the system in the middle, you can never factor this into a product. So you cannot commute these unitaries and measurement operators as you wish. You can commute them a little bit, but not like fully. And then in the end of the day, the map is going to be given by this, where this p of zeta is the probability of observing this trajectory, and it's just the normalization constant. So it's the trace of this whole big thing. And I wanted to talk about two interesting technical aspects of this kind of dynamics. The first is that since we never measured the system directly, we only measured the ancillas, there is never an unconditional back action, which means that if you take this state over here and you average it over all this zeta of t, you recover the original state. So this is a conditional state. It's the state of the system given a certain record. And if you know some information about this record, then of course, it will update what you know about the system. So given knowledge of zeta, it affects what you know about x. But if you average over all zeta, you just get the original x. And this is what we call unconditional back action. And in the end of the day, this is really a no signaling condition. No signaling. I mean, if this was possible, we would essentially be transmitting information faster than light. So this is not possible. The second thing I wanted to mention, the technical point, is that this map is actually not Markovian. So if I go back here, this unconditional dynamics, it's useful because you can view this as a kind of map where at time 1, you just apply a certain map at time 0. At time 2, you apply a certain map at time 1, and so on. So this is very convenient for the unconditional dynamics. You know, you can just update the map from one step to the other. This map is actually not true. It's because this P here is, it depends on the state of the system. So this is not just a completely divisible map. However, and this is a known trick, okay? So this is something that, you know, people that work with continuous measurements, they use this a lot. Even though this map is not Markovian in this sense, we can work with a trace non-preserving map, which is given by this guy. So it's essentially a map where you take the system, you get one ancilla, you apply a unitary between them, and you measure the ancilla. And this map is now Markovian, but it's not trace preserving. So we can actually write an equation like this one, where I'm using here a different row. You see, this is like var row. It's not the same row as I'm using here. Just to emphasize that this guy is not normalized. And so I can take this state, which is the conditional state at time t minus 1, so x t minus 1, zeta t minus 1. I evolve with this map, and this evolution is associated with an outcome z of t. And this gives me the new state, which is x of t, z of t. And that's because, zeta of t can be viewed as zeta of t minus 1, and then z of t. So you take the previous measurement record and you just append an extra bit of information. Okay, and then if you work with this unnormalized state, you actually can write the dynamics as something that is Markovian. And also, you can always normalize this at any time. So you can just play with non-Markovian and non-unnormalized density matrices. And if at any point you want to compute some physical observable, you can just normalize it. And what is cool is that actually the trace of this guy is just the path probability, so the distribution of the trajectory, which is nice. Okay, so now I want to talk about how to characterize the information and the thermodynamics of this kind of system. So for the information, we again have to distinguish between unconditional and conditional dynamics. Oh, and by the way, please interrupt me at any time, okay? So please ask questions if there is anything that's not clear. So for the unconditional dynamics, we have just this state of the system, rho of x of t, which is evolving in time. And the information in the state is just characterized by the von Neumann entropy. For the conditional dynamics, a natural quantity to use is what is called as a quantum classical conditional entropy, which can be viewed as the entropy of the system given the measurement records. And it's defined to be just an average. So you take each state, rho of x of t given zeta of t, you compute the entropy, and then you average this over all possible trajectories. So there is an average here, average over all possible outcomes. And what is interesting about this is not the quantum conditional entropy. So if you guys have a look at Nielsen's book, for instance, sometimes people use the quantum conditional entropy, which is an entropy that can be negative. This is not that. This is a different quantity. So that's why it's called the quantum classical conditional entropy, because it's essentially, this part is quantum. So this object here is quantum, but you're averaging over classical outcomes. So this is just a regular probability distribution. And so this guy is guaranteed to be positive. So this is, let me put this here. Yeah, this is positive. Oh, oops, sorry, yeah. Okay, and then the difference between these two quantities. So if I just compute the difference, S of x minus S of x of t, this is called the Holevo information, or sometimes the Holevo chi quantity. And it has a very, very nice information theoretic interpretation. So you can actually just play with these things here, with these definitions, you can rewrite this in the following way. So it's an average over all trajectories of the relative entropy between the conditional and the unconditional states. So for each possible trajectory, you just compute the distance between what you get when you measure and what you get when you don't measure. And this is the Holevo information. It's essentially saying how much information you have about the system given the measurement outcomes. And I mean, it really has this super, super clear physical interpretation. What is the amount of information you have about the system given these measurement outcomes? And I think this is pretty cool. Okay. Now let me introduce some names here because these things can be confusing. If you read any papers on these kinds of models, there are many informations. There's a bunch of things which are all called information, and it's very confusing. So I'm going to try to give some names to make this clearer. So this quantity here, the Holevo information that we just defined, I'm going to call it an integrated information. It's integrated because it's the information that you get from the net measurement record. So from the full set of outcomes, Z1, Z2, ZT. So you make T measurements and you ask, what is the net amount, the integrated amount of information that you learned about the system? Now, this is different from the differential information gain. The differential information gain is essentially how much information you gain just from the last outcome. So just from this guy. So all you can do is you assume you have one bit of information. How much do you learn from it? And this is naturally defined as what's called the conditional high-level information, which is just the high-level information of X given the last outcome, conditioned on all the past outcomes, condition of zeta t minus 1. And this, it turns out, can also be written as a difference between two high-level information. So this is kind of convenient. You can write this as the high-level information when you have zeta of t, and the high-level information when you only have zeta t minus 1. So it makes sense, right? I mean, it's essentially the extra information that you get when you compare zeta of t with zeta of t minus 1, recalling that, you know, zeta of t is always zeta of t minus 1 times z of t. So it's this extra bit of information. But notice that this is different from the information rate. Now, the information rate, or the high-level information rate, is just the evolution of the high-level information in time. So it's x of t zeta t, and then t minus 1, t minus 1. Whereas here is tt, but t minus 1. So this is the natural change in information. So what this is telling you is how the high-level information changes in time. So is the change in time, change in each step of the high-level information. And so you now have all these quantities. So you have an integrated information, but when you look at rates, you have just the rate of the high-level information, which is this guy, but you also have something which is the actual gain of information. It's how much you gain from only one measurement. And so we can now combine this and write that, you know, the information rate is G minus some quantity L. And this quantity L, we call it the loss rate. And it's essentially just the mismatch between these two. But what is important about it is that it's larger or equal to 0. So this can really be interpreted as an information loss rate. So maybe I should put an information here. Information loss rate. So essentially the information rate is an information gain rate minus an information loss rate. So it's essentially gain minus loss, and both are positive. So G and L are always non-negative quantities. And this is telling you how much you gain at each time step and how much you lose. So this introduces this very interesting kind of competition between the information that you gain and the noise that you introduce. So sometimes if the collision is very strong, the ancilla will completely trash the system. And in that case, you can actually lose information about the process. So it can, if a certain collision is too crazy, it can actually make what you know about the system worse. So this guy can be negative, right? This delta IT can be positive or negative. It doesn't have a definite sign. But the gain and the loss rates, they do, right? So this introduces a clean interpretation for this one. And it
Sorry, Landi?
Yeah.
Just something, I'm not sure if I missed. The information loss, should it have t minus 1 in the second term?
No,
the minus I.
This is a typo. Apologies, you're right. So I guess here it should be x of t. And then let me see, I think zeta of t minus 1.
Yeah, okay, sure.
Yeah.
Just because it needs to be analogous to the information gain, right?
Yeah, no, definitely. Thanks. And in fact, this is good because then you can actually interpret this as the loss rate, because this is like you stop at t minus 1, and this is what you know so far. And then this guy is you evolve one step without measuring. And so, I mean, it's only noise. There is no gain of information because you keep this guy fixed and you only evolve this one. And so that's like one of the intuitions as why this should be positive, because this guy, I mean, you can only make the information worse.
Sorry.
Yeah, Marcelo, go ahead.
I would like to ask a question too about you said that if the collision is very strong or something, you can kind of impact the loss, right?
Yeah.
But once you talked about the gain and loss, the first thing that I thought about is instead kind of the what kind of measurement are you performing in the ancilla? So the question is, does the kind of measurement that you do in the ancilla also impact the gain and the loss? And did you assume any particular kind of measurement scheme?
Right. So we don't assume any kind of measurement so far. We will in a second. So there is, when we talk about thermodynamics, there will be one condition on the type of measurement, but so far it's general. So far, I mean, the map is very, I mean, simply just this one, right? So it's unitary, and then you have this MZ which acts only on the ancilla. That's it. This guy acts only here. The only assumption that we do really is that it acts only on the ancilla. It doesn't measure the system directly. But otherwise, this is just a generalized cross operator. Yeah. So now, the other question about whether the information loss rate is affected by the type of measurement. So I think that's a very good question. Let me see if I can add a page here. Yeah. So this is actually very interesting because so the loss rate is the information at x of t minus 1 with zeta t minus 1 minus the information of x of t with zeta t minus 1. So it's the same, oops, sorry. Yeah, it's the same t minus 1 on both, the same zeta on both, but different x's. And now here's the idea. We can think about the system is here at x t minus 1, and then it evolves to x of t according to some map E. And there is no measurement here. And then sorry, this is zt minus 1, and this is zt minus 1. So let me just be clear. This is like, I'm just denoting this as kind of a conditional state. So it's x of t minus 1 given zeta t minus 1. And then we just apply a map without any measurement, which takes us to x of t given zeta t minus 1. So here, since there is no measurement, this guy doesn't change. All that changes is this guy. And then from here, we actually do the measurement, and then we get x of t given zeta of t. So you see the act of measuring is only on this step. And so this information loss rate at that step is independent of the type of measurement. So it depends only on the map E, right? So that's a good that you mentioned. So it depends only, let me put it this way. So it's independent of M of Z. Make sense?
Yeah. Then is it the same of saying that this quantifies the loss of coherence, like global coherence between system and ancilla?
So I don't know if it's can be associated to loss of coherence. So I think more about it as really, you know, you're colliding with the system and you're just messing up the system. So this is really a direct back action from the fact that the ancilla comes in and collides and introduces noise in the system. So it's really local noise in the system, not sort of shared noise between system and ancilla. Okay. Any other questions? So this idea of gain and loss, it introduces a very, very nice concept, which to my knowledge is almost completely unexplored, which is this notion of information of steady states. So when we work with statistical mechanics, we know about these non-equilibrium steady states, right? So if you have a system and you put it in contact with two baths at different temperatures, for instance, it will reach a steady state, but that steady state is not an equilibrium steady state. It's out of equilibrium because the baths are at different temperatures. So there is a heat flow between them. Now, here is the same idea, but with information. If we run this process for a very long time, we may reach a situation where this is zero. But this zero doesn't necessarily mean that G and I are zero, right? So even though this is this minus this, saying that this is zero does not imply that these quantities are individually zero. All that it says is that they are equal. So if they are equal but non-zero, we say that this is an informational steady state. It's a competition because you're always acquiring information. At every collision, you acquire a little bit of information, but you also introduce a little bit of noise. And these two things, they balance out. So you reach a steady state whenever the amount of information that you're getting balances the amount of noise you're introducing. And so this is very, very similar to non-equilibrium steady states in spirit, but now it's information that's at stake. And I think this is really quite fascinating. And I'll show you some examples, which I think will illustrate this very well.
Gabriel, sorry.
Yeah,
the noise that you are saying is not the noise caused by the measure, but it is the noise caused by the system. So the system, sorry, the environment.
It's the noise introduced by the ancilla. So the environment, yeah. That this would be the environment, and it collides with the system and just shakes the system. So that's what I mean by noise. All right.
It has nothing to do with the measurement itself.
No, it has nothing to do with the measurement. So this loss rate, yeah. So that's a very good point. So the way things are constructed, the measurement can only give you a bonus. I mean, that's something that we really wanted to build the entire framework in this way, because the system will collide with the ancilla whether you like it or not. This part is inevitable, but you can actually monitor the ancilla, and this will give you a little bit extra information. So the measurement never makes anything worse. It can only improve things, and we'll see this. Well, I mean, this is in the end of the day exactly what this G is, right? This is exactly the information gain that you get from this measurement. Okay, so actually, before I talk about the thermodynamics, so I was talking about information, right? Before I talk about the thermodynamics, maybe it's useful if I look at some examples. So I'll show you two examples, which I think illustrate this very nicely. So the first example is the simplest one you can imagine. You have a system and an ancilla, and they're both qubits. So essentially, the system is prepared in some generic state, and the ancillas are thermal, and you measure the ancillas in the computational basis. So essentially, M0 is 0, 0, and M1 is 1, 1. And the unitary U is a partial swap. So essentially, the system interacts via a partial swap with the system, and then you measure the ancilla. Now, what I show here in this first plot is just the dynamics of the entropy and the quantum classical conditional entropy. So what is important to notice is how the orange curve is always below the blue one. So this means that the entropy, given that you measure something, is always smaller. Measuring is always good, right? So this guy can never be above the blue curve, because the way we construct it, the measurement is always says more. It says something useful. In the worst case scenario, these two curves would coincide. And now here I present the information rate, the gain rate, and the loss rate. So you see, initially the system is very far from equilibrium. So the information, both the gain and the loss are very high. So you see, you gain a huge amount of information, but there's a lot of noise. And as time progresses, you gain less and less information. So the differential gain of information goes down, but also the amount of noise goes down. And so the difference between them, recall that this guy is G minus L. The blue curve is first positive. So in this part here, the whole level information is actually increasing at each step. But then afterwards, the whole level information actually starts to decrease a little bit at each step. And in the end of the day, it's 0. So this is in the long time limit, you get that all these 3 quantities are 0. So in this case, there is no ISS, because G of infinity is L of infinity is 0. So there is no informational steady state. Now, is this okay? Any comments about this? I'll talk about the other plots later on. I just wanted to show these two. Okay, so now I'm going to introduce something which is kind of nice. My ancilla is actually made up of 2 parts. So what I call Y is actually has 2 components. So you have YT1 and YT2. So it's Y of T is something like this. There's 2 components to my system. And I only measure 2. So, sorry, 1. So I measure this guy, again, in the computational basis. But I don't measure this guy. The logic here is that you can think about this as a kind of register. It's, just like a classical bit that you want to register some information. And this guy is a quantum guy. So you prepare this in the plus state. So it's a quantum resource. And the system interacts sequentially. So it first interacts with this one, then with this one, again, both with partial swaps. And now what you see here is that if we again plot the information and the quantum classical conditional entropy, the unconditional and the quantum classical conditional, we again see that blue is above orange. That's fine. But what is interesting is if we now look at the gain and loss rates. So you see the picture is similar to what we had before. Initially, G is big and L is smaller. But then as time progresses, they change sides. And so the blue guy it's initially positive and then becomes negative. But what is new now is that these 2 curves, they don't tend to 0. They tend now to a value here, which is different from 0. And so this is an ISS. In an ISS, the information rate is 0 because that's what definition of a steady state is. So steady state is equivalence. A steady state is a synonym of having delta I equals 0. I mean, this will always be true. But the orange and the green curves, they don't have to tend to 0, and they don't. So this becomes an informational steady state. So here, you're constantly acquiring information, and you're constantly injecting noise. And the reason why this happens is because we now have 2 ancillas, but we only measure one of them. So the system actually never thermalizes. This is exactly like a swap engine or these 2-stroke engines, the thermal engines that we play with. The system interacts with this one, then this one, then this one, then this one. So it's never in equilibrium. It can never really thermalize with one or the other. It's always bouncing back and forth. And so you reach an informational steady state because you're constantly getting information out of this. Yeah, makes sense? Okay. And now finally, I want to show something which is even cooler. So this is the same example as before. But now what I'm going to do is I will just choose initial state to be the ISS. So sorry, it's not the ISS, to be starting from the unconditional steady state. Sorry, this is a typo. The idea is this, you see, I start from a generic state. I just, choose some weird state and start from it. So the curves de-evolve. But now after a long time, these curves, they will saturate at some point here. And what I do in this case is I start from that point. So essentially what I'm doing is I turn on the system for a long time, but I don't measure it. And then only after some time, I start measuring it. So it's a little bit like, here is time, sorry. Here is time. And here is, let's say, the state of the system, like this, right? And so the idea is that initially it goes like this, and then it saturates. But now at a certain point, I start measuring. So here I start measuring. And then what happens if we call this S of x of t given zeta of t, is that this will be like this, and then it's going to fall down. Right? So the information that the entropy about the system goes down. So initially it goes up because we're not acquiring any information. And then when we start measuring, the information goes down. And so here, this is what this is shown. So the blue curve doesn't change anymore because we are already in the unconditional steady state. But the orange curve, it starts going down. So as soon as we start measuring, it starts going down. And the same is true for G and L. So as soon as we start measuring, these quantities, they start to change and they saturate to a conditional steady state, to our informational steady state. So that's the basic idea. Any questions? Okay. So now the second part is I'm going to talk about the thermodynamics of this. So I'm going to use this by now famous formulation of the second law, which states that the entropy production in one collision, for a single collision between x and y, is essentially the mutual information, the quantum mutual information between x and y, and the relative entropy. So here, this I of x and t, sorry, xt, y of t, is s of rho x of t plus s of rho of y of t minus s of rho of x of t, y of t. So this is really the quantum mutual information. And this can be written like this. So as just the change in entropy in the system plus the entropy flux, right? So this guy here is the entropy flux. And it's given by this combination. Is the change in entropy of the ancilla plus the relative entropy in the states of the ancilla. And sorry, I forgot to mention here, this prime, it means the state after the map. So essentially here, what I have in mind, let me just write this down, is essentially rho xy prime is the trace, sorry, yeah, it's u rho x rho y u dagger. That's what I mean. And the entropy flux can also be written in this way. So this is just a substitution. If you open up these formulas, you see that they simplify and you get this guy, right? And so this can be viewed as a difference, a change in the thermodynamic potential log of rho y. So you see, this is the changing state of the ancilla, like the initial state and the final state, and you have here log of rho y. So if this rho y is e to the minus beta hy over zy, then you get that the flux is going to be minus beta times delta heat, delta Q. But we don't assume that. So we're not assuming that the ancilla is thermal. The ancilla can be anything. And so this flux, it doesn't have to be the standard thermodynamic entropy flux. It can be anything. So this refers to the unconditional dynamics. I am being a little bit careful. I'm putting this superscript U here to refer this to the unconditional dynamics. So no measurements. And we can now compare this with the conditional dynamics. So in the conditional dynamics, what we want to do in the end of the day is we want to define entropy production and flux, and we want to define the such that they satisfy this, right? So we want to have something where in analogy to this formula, where the entropy production is the change in entropy of the system plus flux, we want to have the entropy production to be the change in entropy of the system plus flux, but now it's the conditional entropy here. But this is just a definition. This doesn't say anything. What it says is that if we can somehow determine what one of these two quantities is, then we can determine the other. So if we could somehow figure out what the entropy production is, then this establishes the flux and vice versa. So the natural choice that we believe is correct for considering the entropy flux here is to actually define the conditional flux as a generalization of this formula. So here we have just the change in entropies or relative entropy of the ancilla. And here we have the same thing, but everything conditioned on a single outcome Z. You know, it's important that here is only Z, is not zeta, because the entropy flux should be a local quantity. So this is depends only on that outcome Z. However, if you open this up, and again, it's really just a matter of opening up and the definitions, you see that most things simplify and we get this simple formula over here, which is very similar to the unconditional flux. So if you compare this with this, they're very similar. The only difference is that while in the unconditional flux, we have here a row of y prime. Sorry, this is a little bit small, but I guess you can see here y prime, meaning final state of the ancilla. Here we have this row tilde, which is the final state after it undergoes the measurement channel. So it's essentially, you have rho y prime of t, and then you undergo the measurement, m, and then you get this rho y tilde of t, right? Just the average over this quantum channel. So the only difference, if we define things in this way, between the conditional and unconditional entropy fluxes is that the unconditional depends on the final state of the ancilla, and the conditional one depends on the sort of processed final state. So it's the final state after being processed by this quantum channel. Yeah, sorry. Yeah, so this is the same. This is the same as was in the previous slide. And what I want, let me just scrap this. This is not good. So let me just write down the formulas here. So delta phi t u is trace of rho y minus rho y prime t t log of rho y t, and delta phi t c is equal to trace of rho y t minus rho y t tilde log of rho y t. So you see the only change, I'm going to even highlight this, the only change is here. Here. And here. Yeah. So, and of course, almost where, and yeah, let me write this down. Rho yt tilde is sum over zt mzt rho yt prime mzt. There. So, I mean, unless we have a very strange measurement, this guy will definitely be different from this guy. I mean, it's you choose a generic measurement for your ancilla, and this will definitely change the state of the ancilla, right? However, very often we will have that this quantity is actually equal to this quantity, because this will be true whenever the measurement strategy doesn't affect the populations in the initial basis. So all that matters is that we're measuring in a certain measurement which doesn't affect the populations of this state in the initial basis of this state. So for most kind of reasonable measurements, these two quantities will actually be the same. And if they are the same, then this means that the two fluxes are equal. Now, there is a very intuitive explanation as to why this should be the case. I mean, this is a flux. A flux is a physical quantity. It shouldn't depend on subjective information. The other things we're talking about, they are subjective. They depend on whether or not the experimenter wants to read the measurement or not, right? The ancilla interact with the system anyway, but the experimentalist can choose to measure the ancilla or not, to acquire the information or not. So that's a subjective thing. And the flux should be a physical quantity, so it shouldn't depend on the choice of the experimentalist. It will only do so if the very act of measuring the ancilla causes an additional flux. So this could happen, for instance, if you choose a very strange measurement where the measurement itself perturbs the ancilla in such a way that flows entropy to it. So if there is an entropy flow to the ancillas, then the fluxes will be different because you chose a weird measurement. But if you choose a passive kind of measurement, then you shouldn't affect the flux. So we're going to assume this from now on, and this is the only restriction that we impose on the type of measurement. This measurement is still very general. The only thing we assume is that it satisfies this. Okay, and so finally we get these results. So we get that here. I'm just summarizing them. This is the unconditional entropy production. Is change in entropy plus flux. And the conditional entropy production is change in entropy plus flux. But you see, now it's the same U that appears here. It's not a C, because these two guys, we're going to assume that they're the same. And so if we just do this one minus this one, we actually get the difference in the thermodynamic entropy productions is associated to the change in Holevo information, the Holevo information rate. So this provides a very, very strong connection between thermodynamics and information gain and loss, right? So essentially, what differentiates unconditional from conditional second law is essentially the information that you are acquiring. And we also show, this is a little bit technical, that this difference is still positive. So the conditional entropy production is still a positive quantity. Now, if we look at the integrated information, so we just integrate both of these quantities from time 1 to t, we naturally get that sigma tc is going to be sigma tu minus I of t, right? And so what this means is that if we consider the integrated entropy production, this will always be smaller than the unconditional one based on the information gain. So this is cool because it means that conditioning always makes the process more reversible. So you can all, conditioning can only make things better. You can only make the process more reversible because you gain some extra information. And so the intuition that I have is that essentially the entropy production is measuring the irreversibility of a process. And part of that irreversibility is associated to our lack of information about the bath. So there's some stuff about the bath that we don't know. And when we measure it, the ancillas, right? When we measure the ancillas, we actually learn something. So we mitigate a little bit this irreversibility. We make the process a little bit more reversible. And that would be the basic idea.
Gabriel, can I ask a question about that?
Of course, yeah.
So the formula of unconditional entropy production that you departed from is related to this kind of fluctuation theorem that you assume like that you make a measurement, a 2-point measurement in the bath, and the kind of the second measurement that you make is in the same basis that in the first one. But then when you do this business of conditioning the state, you do not make like the same measurement scheme. So my question is this difference in information, can it be cast in terms of the difference of the two schemes of measurement?
That's a very good question. I don't know. So this is something that we at some point we were thinking and doing some calculations about like the stochastic version of how to construct these quantities. So we know how to construct this guy stochastically, and whether we could construct this one as well. But it became a little bit too complicated, and so we stopped. We decided to not work with fluctuations at all, just focus on the averages. So I have no idea how to construct this guy from a generalized TPM scheme or something. But that's actually a very interesting question, and if you could address that, I mean, that would be a paper in itself, I think. Yeah. Okay, so if there are no other questions, so just returning now to some of these plots. Here's the example with a single ancilla where there is no ISS, no informational steady state. And so what here I plot, for instance, the conditional and the unconditional entropy production. You see that they start very, very high because you're producing a lot of entropy. The process initially is very irreversible, but then as time progresses, they both go down and they tend to zero. And the integrated versions of them essentially grow at first, but then saturate at a certain value. So for very long times, I mean, you just have a final value of the entropy production and that's it. And this mismatch between them, so the mismatch between the blue and the orange curves is exactly the whole level information. So yeah. I'm not going to comment too much about these guys, but these are the stochastic versions of these three quantities. So you can make stochastic simulations where you just sample using Monte Carlo these trajectories, and these are just sample trajectories of these three quantities: the rate, the gain rate, and the loss rate. Now, in the case of two ancillas, what we get is that the entropy production rate now tends to a finite value. So you see here it tended to zero because there is no ISS, so it just tends to zero. But here it tends to a finite value, a non-zero value. And similarly, the integrated entropy productions, they keep on growing because the system never reaches a steady state. It just keeps on growing and growing and growing. Yeah. And here is the same thing. So let me see if I should talk about this one. Okay, I'm not going to talk too much about this one because it's already getting late. But this is just to show that you can actually do these things in the single shot scenario. So for instance, I think this is the interesting guy. This is the outcome. So the outcome of each measurement, Z is 0 or 1. And this is the moving average, right? So this is just, the moving average. So you can imagine that Z is just oscillating between 0, 1, 0, 1, 0, 1, and so on. But here's like the average. So you see that as time progresses, this tends to an average value. So this is the average Z occupation in the steady state. And you can also do the same thing, for instance, with the gain rate. So the red curve here is the gain at each step. So at each step, how much information you gain. So you see that it oscillates a lot. But the blue is the moving average. So it's the average information that you gain in the steady state. So in the ISS, you're actually gaining this amount of information at each step on average. And finally, I want to illustrate this in the context of this specific example, because I think it provides a nice idea of what's happening. So the experiment, which was run in Copenhagen, is an optomechanical system. And so you have, just like the picture I showed in the beginning, you have an optical cavity, but the system in the middle here, X, is a mechanical mode. So it's a mechanical mirror. And essentially, this X is interacting with a laser field. Now, the idea is that this system is going to reach an informational steady state. And the way this is done is because you're constantly acquiring information from the laser, and you use the information to locate the position of the mirror better. So by measuring the photons that leak out, you can have a better assessment of the position of the mirror. And the way this is done is by talking about variances. So in this case, essentially all that we talk about entropy before is essentially pretty much replaced with the variance. So we have sigma u and sigma c. So this is a continuous variable system, and it's more convenient for the experimentalists to work with the variance. So this is the variance in the position. And so the idea is that, you know, if you have a lot of uncertainty about the system, the variance is very large. And if you know a lot about the variance, about the position of the system, if you have a lot of information, the variance is small. Now, what happens is that essentially, let me see how to put this. The idea of what they do is a little bit like this. So here is the position and the momentum of the oscillator, right? And you can imagine that this oscillator is moving around. So it's a Gaussian, a little bit like this laser pointer here. Well, it's not a laser pointer; it's just pointer, but a little bit like this pointer, and it's moving around erratically. So the mirror is vibrating, and so this thing keeps moving around. Now, if you don't measure this, what you're going to eventually observe is something like this, right? Wait. Yeah, this is better. Something like this. So if you don't measure it, you're just going to observe one big Gaussian, because the system can be everywhere. So you observe one big Gaussian. But what they do is they use a kind of feedback loop. So it's a very clever trick. They use a feedback loop, which works as follows. So suppose that the position is like here. And if they measure that it's here, they apply a force to the oscillator, which brings it back to the middle. Then it starts wiggling again. If they sense that the oscillator is here, they apply a force and they bring it back to the middle. If it's now here, they apply a force and then bring it back to the middle. So they're measuring the position of this oscillator in phase space, position momentum. And depending on the position, they apply the appropriate displacement and always bring it back to the middle. So no matter where the oscillator is, they're always trying to push it back to the middle, which is super nice. And by doing that, instead of having this big Gaussian, you just have a smaller Gaussian in the middle. So in the end of the day, you're just going to have like a smaller Gaussian like this, right? Something like this. And so essentially, in the ISS, the system is colder, right? So this is what's cool. So in the ISS, the system is colder. You measure, you cool it by measuring, right? Essentially, by acquiring information, the system will appear to you as being effectively colder than it previously was. And this is actually one of the most efficient ways of cooling these mechanical mirrors. So we discussed a paper on the archive review the other day, which was talking about these cooling of mirrors for gravitational wave detector experiments, right? And there are many, many ways that you can cool down the vibrational modes of a mirror. And this is actually one of the most efficient ones. You cool it by measuring. And the ISS is the theoretical framework for describing this type of process. So here is the example. Here's the experiment. So we characterize entropy flux and entropy production. So this is flux and this is production. And this is done at the trajectory level. So we have the individual stochastic trajectories of entropy production and flux. And the darker blue curve here is the average. And so you see that initially there's a transient and it tends to a steady state where you have a finite entropy production and a finite entropy flux. And here is the information gain and loss rates. So yeah, the signs here are flipped. So the signs are flipped. Sorry about that. But essentially, this is the whole-level information rate, the gain, and this is the loss. And so you see that the zero is here, right? But if you look at the gain, or made the laws, you see that they're both not at zero. The information, the whole level information rate tends to zero, but these two guys, they don't tend to zero. So you tend to an ISS. Right? This is the signature that you have an ISS. Okay, so that's pretty much the idea. The take-home message is collisional models which are continuously monitored. And the cool thing about this is the idea of an informational steady state. It's a steady state which is only maintained because you're constantly acquiring information. If you stop measuring, the system would drift away. But as long as you keep on measuring, the system will stay in a non-equilibrium state. So you keep it in a non-equilibrium state because you're constantly acquiring information. So that's the idea. Thank you. And sorry for taking a bit too long. But I think this is fine. This is not too bad. So any questions?
Gabriel, I think I lost the most important part because if you have information of steady state caused by the measures, it is the system physically itself. It's at a steady state caused by these measures, or you describe your subjective state of the system get on this steady state.
Right. So it's always a subjective, right? I mean, whenever we write a density matrix, that's always subjective. The density matrix is always encompassing the best knowledge that we have about the state, right? So in the end of the day, it's always subjective. And then the ISS, I think this is a good example. Like here, like if you don't measure the position, you will assume that the system is in a big Gaussian. But when you measure and you can actually correct this, you realize that the Gaussian is not so big. What happens is that, let me take this one out, is that this big Gaussian is actually a bunch of, oops, sorry. Let me see if I can do this. It's like a bunch of smaller Gaussians placed together, something like this. Yeah, I saw a drawing about this in a paper once, and maybe I should do a better one. But the idea is that the system is always in a small Gaussian, like the small red one. But this small Gaussian is moving around, right? So it's like just wiggling. And so if you don't know its position, that what you realize is that it's in a big Gaussian, but it's actually in a smaller one.
The big Gaussian was our ignorance.
Exactly. Yeah, so any probability distribution is ignorant based, right? And so if you have a mixed state density matrix, it's going to be, it is subjective.
I have a question. What determines the time scale to reach the steady state?
Right, that's a good question. So I think there is one time scale, which is just the intensity of the interaction, right? So let me go back to the beginning. You have these unitaries here, U, and depending on the intensity of these unitaries, this will definitely determine the time scale, right? So if the system interacts very weakly, for instance, with these, we're never assuming that the measurements have to be weak. They can be weak or they can be strong. But if they are strong, it should reach a steady state quickly. But then there is another thing, which is this is the time scale associated with reaching a steady state. But this may be different from the time scale of reaching the informational steady state, and that may be associated with the type of measurement that you do. You can, for instance, make the system interact strongly with the ancilla, but you only measure the ancilla very weakly, and that should also play a part. But it's not exactly clear to me how to separate these two things.
I see, thank you. Because I got curious, like when you talk about cooling strategies, how to optimize the time scale to cool your system.
Yeah. That's a good point. So for these optomechanical guys, it's really the coupling. So it's the strength of the unitary. Their figure of merit is exactly the strength. So usually they have a figure of merit, which is like the some kind of coupling constant divided by the damping. Something like this. So it's essentially the strength of the sorry, yeah, let me be more clear. So let me, yeah. So it's the mechanical optical coupling divided by the optical damping. So essentially the time scale for them is associated to how strong light interacts with the mirror, but they also take into account the fact that this light here is damped, so there's a leakage of photons, and this makes the problem the whole thing worse, right? It's better if leaking was smaller. So that's usually the time scale that they play with. In this, I guess I could answer your question for this model actually. I mean, not right now, but for this model, you actually have only like a few equations that you have to take into account. So let me see. Let me put this here. So one of the equations that you have is the unconditional variance, which is just given by this. Sorry, yeah, sigma u steady state minus sigma u. So the unconditional variance, it evolves like a very simple differential equation. And then the conditional variance, it evolves according to this equation, which has a nonlinear term. So we can very easily determine the time scale associated to the unconditional dynamics, because it's just related to this thing here, which is the damping constant. But if you now go to the conditional dynamics, this is a nonlinear differential equation. And so it's a little bit more difficult to determine the time scales, but I think it can be done. Yeah. Any other questions?
Gabriel, you mentioned that in this setup, the entropy production is, or the entropy is related to the variance, but is there a equation relating them, or is it something phenomenological? Or?
No, yeah, there is. Rodolfo will know all about this. But essentially, if you have the covariance matrix, which is like sigma average of q squared, and then here you have the average of qp average of p squared, like this. Then the Renyi-2 entropy of the state is 1/2 log of the determinant of sigma. That's it. And then the von Neumann entropy is very close to the Renyi-2 entropy, but it's also a function of sigma. It's just a more complicated function. It's related to something called symplectic eigenvalues. It's like, but it's still a function of sigma. The Renyi-2 is very easy. It's just the log of the determinant. That's direct relation between variance and entropy. For this experiment, they made the system in a way that the covariance matrix was something like this. So they constructed it in a way that these off-diagonal elements are 0 and these two elements are equal. And so this is just, like a number, sigma 0 of t times the identity matrix of time 2. So for them, they have only one variance. They don't have a covariance matrix. It's just one variance. It's more convenient. Any other questions? Okay, then I guess that's it, guys. Thank you. And so next week we have Naim. Yeah, and again, if you want to say something about your work, send me a message. We should try to make this a weekly thing. Yep. Ok, voltando em português então. Valeu, pessoal.